Hello everyone, welcome to the fourth episode of our serie ROS2 Basics. In this episode, we'll dive into one of the core concepts of ROS2, the topics. We are going to understand their purpose, how they work, and how we can publish and subscribe to them. We'll first interact with topics using the terminal, then with C++ Node. For those who have followed the previous episode on topic with Python, you can go to the following timecode to start directly with C++ Node. The concept explanation will be the same. As explained in the first video of the series, ROS2 has a distributed architecture. This means that ROS2 systems are made up of several nodes communicating with each other, where each node has a precise function. There are three fundamental ways for nodes to communicate: topics, services, and actions. In this episode, we will focus on topics, as this is the simplest method. It will be used to exchange data quickly in one-way communication. Topics are used for all continuous data flux, such as sensor values, low-level commands like speed control, and robot state, like its position. It could be considered as the default communication method to use if you don't have specific needs such as feedback, synchronous or asynchronous behavior. A topic is a channel where nodes can send and receive one type of message. The basic example is one node, the publisher, sends message to the topic, and another node, called subscriber, receives this message by subscribing to the same topic. Each time a message is received by the subscriber, an event named callback that executes a function is triggered. A lot of different configurations are possible: one-to-one, one-to-many, many-to-many. Every message sent by a publisher on a topic is then picked up by any subscribers that listens to that topic. The message exchange on ROS2 topics are interfaces that follow specific structures, such as simple type like integers or strings, or more complex type like arrays or custom-defined message. In the examples of this video, we will use the string, twist, and laser scan message, which are built-in message in ROS2. You can view them with the following commands: ROS2 interface show, the package name, /message, / the name of the message. Let's use the command line interface to do our first manipulation with topics. First, you can check for available topics using the command ROS2 topic list. There are only the default topics used by ROS2. Now we publish the data on the topic example topic with the command ROS2 topic pub. So ROS2 topic / topic name, message type, then the message to send. It will publish in loop our message until we stop it. If we do ROS2 topic list again, we'll now see the topics that we are publishing on. We can subscribe to this topic with the command ROS2 topic echo / the topic name. It will display the message received. If we use the command ROS2 topic info, we can see the type of the topic, the number of publisher and subscriber. If you use the same command with the argument v, you will have more detail like the name of the nodes and their QoS. QoS is a settings for ROS2 communication. We'll talk about QoS in future videos as it's a more advanced topic. For now, we'll use the default QoS of ROS2 communications. Now that we have seen how to use CLI to interact with topics, we'll create C++ publisher and subscriber nodes in our C++ package. We are going to publish a string from a node named TextPublisher on the topic example string topic, and subscribe to this topic on a node named TextSubscriber. This subscriber will print the received string in its callback. Let's create a publisher that will publish on the topic example string. Let's break down the code. We start by including the required libraries to create our node: memory, which provides the support for smart pointers, which manage the memory automatically; RCL-CPP, which is the ROS2 CPP client library to access to all the ROS2 core functionalities; and we import the string message type from the std message package to be able to use it in the node. We define a class TextPublisher that inherits from RCL-CPP node, the ROS2 model class for C++ node. We declare in private the variables that we are going to use: a publisher, which is a shared pointer of type RCL-CPP publisher, and we indicate the type of message that's going to be published; a timer that will be used to call a method periodically; and a simple integer to store a counter. Then we declare the constructor in the public section of the class to initialize the node and provide the name TextPublisher. The counter is also initialized to 0, and it will be used to display the number of messages published by the node. We initialize the publisher and indicate the message type, the topic name, and the QoS settings. As we want to use the default ones, we'll only need to set the queue size and we set it to 10. Here, the publisher is create and we publish the message of type string message. The queue size is the number of messages to keep if they are faster than it can be handled by the subscriber. That will be processed once the subscriber can do it. Then we initialize the timer to call the timer callback function at every second. We use the std_bind to assign the method timer callback as a callback to this timer. In the timer callback method, we increment the counter, create a message of type string, set its value using our counter value plus a static string, then we use the method publish in our publisher to publish the message. At the end of the file, we add the main function. We initialize the ROS2 client, create a node text publisher that will be wrapped in a shared pointer, then we use the spin command that keeps C++ from exiting the node until it's stopped by the user. Our node is finished, so we need to update the semek_lix.txt and the package XML to make the node executable after the compilation. We can remove the parts that are not required, then we add find package std_message because we need this dependency in our node. We add the lines add executable to indicate the name and the file of our executable, and the amend target dependencies to provide the dependencies to our node. Then we add in install target our executable to make it available in our workspace after using the source command. Then, in the package XML, you need to add this tag to add the new dependency std_message. We can now build our package with the following command. We can run the node with the command ROS2 run cpp ROS2 Basics text publisher node. We can see that the data is published, so our publisher is working fine. Now we will create a subscriber node that will subscribe to the same topic. Let's check the code step by step. The subscriber follows similar structures than the publisher on the node declaration part. But this time, we'll declare a subscriber that will handle the same message type string. There we have the subscriber declaration. We need to indicate the message type, the topic, the callback function, and the QoS settings. There, we will use the default QoS with the queue size of 10 to match the publisher. The good practice is to have the same QoS settings for the publisher and the subscriber. We create a class attribute of type string to store the data from the topic. Then we have the callback function. As said before, this function will be called at every new message received. The method has for input argument the data sent by the publisher. So we get the value of message data, which is the string sent by the text publisher. The node is finished, so we can modify the semek_lix.txt to add the subscriber as an executable. Then we compile a new terminal using the following command. Then we can try to run the node with the following command: ROS2 run cpp ROS2 Basics example subscriber cpp. You can see that at each new message the callback is executed and the value of the self last message is updated. Well done, you have created your first publisher and subscribers node in C++. We are going to finish this video with a practical example of topic utilization to interact with a robot in simulation. We are going to install Gazebo Sim in order to simulate a robot. Be careful, there is two different Gazebo, Gazebo Sim and Gazebo Classic. We can download the package with the following command. It will install the version of Gazebo that match with your ROS2 installation. If you have installed ROS2 Jazzy, it will be Gazebo Harmonic. I will put in description a link with the correspondence between ROS2 and Gazebo Sim versions. Once you have finished installing Gazebo packages, you can install the zero-diff drive package by cloning the repository in your workspace. The link is also in description. You need to build and source, and then you will be able to start the simulation by running the following commands. If you are interested about a tutorial on this robot simulation, let me know in comment section. Now we are going to create a node that is a publisher and a subscriber in the same time. It will subscribe to the topic scan to get the laser scan data from the robot and publish to the topic cmdval, which is by convention the topic to send a velocity command to the ROS2 robot. In our case, the robot has a publisher on the topic scan and a subscriber on cmdval. Our node will be the subscriber on scan and the publisher on cmdval. In this code, we will subscribe to the topic scan to get the scan value in front of the robot. As long as the distance between the robot and the obstacle in front is greater than 0.5 meter, the robot moves straight at 0.2 meter by second. Once it's closer than 0.5 meter, the robot must stop. Before starting our code, we check the topic available with ROS2 topic list. Then, we check the topic that we are interested in. So ROS2 topic info scan and ROS2 topic info cmdval. We can see that the topic scan is a laser scan from the sensor message library and the cmdval is a twist message from geometry messages. We start by creating our publisher on CMDevel and our subscriber on the topic scan, as we have done in the previous example. We also define a timer that will update the command of the robot every 0.2 seconds. We create a callback function of the subscriber to get the last updated value from our laser scan, and we get the middle value of our laser scan to get the distance of the obstacle in front of the robot. Then we create our timer callback named control loop, where we check our front distance. If it is smaller than 0.5 meter, we publish a linear command velocity of 0 to stop the robot. Else, we publish a linear speed of 0.2 meter by second. Once again, we need to modify the semaklis.txt and the package XML to be able to compile the node. Then, we compile with the following command. Let's test the node with the command ROS2 run. You can see that the robot is moving, then stop when it's close enough to the obstacle. Your node should work as expected. Congratulations, you have finished this tutorial on topics, publisher, and subscribers. In the next episode of ROS2 Basics, we will cover the services. Let me know what you think about this format. Do you prefer a separate video for Python and C++ or a longer one with both? Be sure to like, subscribe, and turn on the bell to stay informed about ROS2 Basics series and upcoming videos. If you have any question or topic to suggest, leave a comment. See you next time!